So we now know about the existence of this new type of integral, and we know at least one example of why it's useful to calculate the work done. I'm going to dedicate this full video on how to find dr vector, the differential displacement vector. Okay? So let me refresh your minds that we have a curve C, and the differential displacement vector, well, remember that curve C is given by some function r of u, right? That is the parametric equation for a curve. So then if we fix a certain value of u, r of u is some vector that points from the origin to that value of u. This is r of u. And if we now increase our slider is our parameter, we increase it by a tiny amount du. So therefore, the position vector will increase by a tiny amount along the curve. So it will be r of u plus du. Here I'm exaggerating it because then it's easier to draw, but in reality it would be a tiny increase, yeah? R of u plus du. So then the subtraction of these two vectors, r of u plus du minus r of u, gives us this vector here, which joins the initial and the final point, and this is dr. Okay? And this is a vector which is proportional to the rate of change of the position with respect to u, and it's pointing in the direction tangent to the curve. Okay? So how to find it? As usual, you are already getting used to this, I think. The first method is look it up on a table. Look it up. For typical shapes. For example, the dr, if the curve is a circle, that's very easy. So let's have a look at the table. So in the exam, we have this table, and you have already used ds and dv. So now we are going to use dr vector. And you can see now that this is a vector. So this is exactly what we need. So for example, let's say our curve is a circle in the xy plane. So we are in polar coordinates. We are fixing rho equals a constant radius r, and phi is a variable, and z is equal to 0. So both rho and z are constant, so d rho and dz is 0. We are not changing rho and we are not changing z. So we are only left with this, and this is dr. Okay? So that's a way of finding dr vector, the differential displacement. Another way to do it is to use geometrical intuition. So for example, if we go back to the example of a circle, okay, we are moving around the circle. So you already know what dl is. dl is r d phi, right? It's how much you move when you increase the angle by around d phi. But now we know that dr has the same length as dl. So actually I can write this nice equation that I didn't write earlier. So dl can be defined always in general. dl, the scalar dl that we were finding in the previous videos, can be defined as the norm of this dr, okay? Which means that dl is just the length of dr vector, okay? So therefore, dr is simply dl in the direction tangent to the curve. And what is the direction tangent to the curve? What is the unit vector tangent to the circle? Well, that's given by E phi hat, right? So therefore we can just write E phi hat. So this will be equal to r d phi E phi hat, which coincides exactly with what we saw in the table, right? So that's a way of doing it. Finally, if you don't like looking at the table and you don't trust doing it by geometrical intuition, you can always use the recipe, mathematical recipe. And the mathematical recipe is very simple. You start with your parametrized curve. You find the derivative with respect to u, the parameter. So this will be basically dx over du, dy over du, dz over du. And then you just say that dr is equal to this vector that you found, yeah, multiplied by du. Okay, so this is the master equation that you can use to find dr vector, the differential displacement. Okay, so that is great. Now, of course, it's very easy to remember this equation because it's as if the du's cancelled out, right? So then you are left with dr only. Also, this definition fits very well if you remember the definition of the derivative of a vector with respect to a variable was defined as the limit when du goes to 0 of r of u plus du minus r of u divided by du. So if you multiply this by du, you're simply getting this and cancelling this out. And this is exactly the vector that we define as dr. Yeah, is the subtraction of r of u plus du minus r of u. I am showing you the same thing in 1,000 different ways. And the reason I do this is that I want you to understand that every piece of the puzzle fits perfectly. Okay? I hope I'm not confusing you, because you can just follow any of these routes. It doesn't matter which one you follow. I just want to make sure you understand that everything fits in the puzzle. Okay? For example, you remember that the equation for dl in previous videos for normal integrals dl was the norm of dr over du times du, right? So this makes sense if you now know that dl is simply the norm of dr, because if you substitute dr as you have here, so that's just the norm of dr over du times du, and if you take du outside, you end up with the definition we were using for dl initially. Okay, so everything should start making perfect sense. So sometimes the fastest way to find dr is by using the definition. So first you find the parametric curve, then you do the derivative, and then you use this definition. Sometimes that's the easiest, but sometimes it's not necessary. You don't have to do that, because you can just find dl, which is intuitive, and then just add a unit vector in whatever direction is tangent to the curve. Okay, so sometimes that is easier. But in the end of the day, all of the paths lead to Rome. In other words, all of these methods lead to the same answer. Okay? So that is how to find dr. In the next video, I'm going to try to give you a geometrical intuition of how does this integral look like? So what it is that we are integrating. So see you in the next video.